So my presentation would be a little bit different from the previous one in the sense that I will try to give an overview of what electroactive polymers are, and especially the special kind of actuators that can be made out of these materials. And in particular, the aim of my talk is to try to provide an insight on opportunities, new opportunities for biomaterials and tissue engineering, which might come from this field. So, as we all know, biomaterials today are a very heterogeneous field with many different kinds of materials, functionalities. What we are looking for here is a functionality that is missing. And this functionality concerns artificial muscle properties. And this is important because artificial muscle materials might actually provide something new, might add new functionalities to conventional materials in order to enable a variety of applications that today are very challenging, or in some cases, not really feasible. Here we have just a couple of examples of prosthetic arms, which today are made of steel, aluminum, all sorts of metals, and some components also plastics, but they are still very far away from the natural biological tissues that make up a natural arm. And similarly, we can find many other kind of applications, for instance, artificial eyes, which are still, more science fiction than reality. So, what can we do at material level in order to enable those new functionalities? Well, first of all, we need a combination of key properties. The first one is certainly actuation, in particular electromechanical actuation. So a way to use new materials in order to convert electrical energy into mechanical energy, so forces and displacement. Moreover, we need mechanoelectrical sensing because our natural muscles actually are able to self-sense their own state. Moreover, we need stiffness control because, again, natural limbs, natural muscles have a compliance that is naturally controlled by the central nervous system. So these properties, moreover, have to be combined in a piece of matter that is viscoelastic in order to mimic the mechanical characteristic of biological tissues. So if we are able to combine all these properties together, we end up with what we call an artificial muscles, that of course is functionally analogous to natural muscle, but not necessarily structural analogous. And I'm going to describe you something later on. So how to address those needs? Actually, our group, at least this field, we are addressing them with electromechanically active polymers. So a kind of materials that are able to change dimensions and or shape when an electrical stimulus, a proper electrical stimulus, is provided. The most typical and most performing example of this family of materials is called the electric elastomer. The electric elastomer are quite a new entry, quite a recent entry in that field, a couple of decades ago now, which are really the best performing at present, and I will focus my presentation actually on them. But in reality, the whole field of electroactive polymers, or electromechanically active polymers, as I like to call them, is actually including two big families. One is called ionic polymers and the other one electronic, because they are differentiated according to the charge carriers. In the first one, they are ions. In the other ones, the second one, they are electrons. And the second family includes materials that maybe are familiar to many of you, like piezoelectric polymers, for instance, or electrorestrictive polymers. And then we have these electric elastomers, which, as I said, are the most performing one, and I will focus on them. There is also another family, which historically is the former, actually, the ionic one, which again includes materials that are very well known, like electrolytic gels or similar material, like they're called ionic polymer metal composites, or even conducting polymers, for instance. There are also non-polymeric materials like carbon nanotubes, which belong to the same family because they have similar principle of operation. Just to give you an example of the first family, what can be done with them? For instance, this is an example of a gel that swells in an environment where the pH is controlled, but you can actually change dimension even in response to electric field, magnetic field, different chemicals, and so on. And you can actually harvest those motions those deformations in order to create motion. This is an example of another ionic polymer family, which swell basically when some electrolytes from an environment intercalate within the polymer, when a voltage difference is applied between two electrodes. I'm not entering the details because this is not the focus of my presentation, but just to give you an overview of what is available, especially if any of you has heard about them. You can do nice things with those materials. This is just one example. I wanted to mention it because it is very interesting. It is a steerable catheter where basically the walls of the catheter are made out of these materials, ionic polymers, which bend when a proper voltage in the order of 1 volt is applied to them. And this is nice, this is useful because one day, this is not commercially available yet, but one day they might be actually used to properly steer the catheter inside the human vasculature with higher accuracy and higher safety for the patient. The advantages of this technology are the low driving voltages. I just mentioned 1 volt. The drawbacks, by the way, are the fact that the strains are typically relatively low, in the order of 1 to 10%. And unfortunately, the materials have a poor stability, low response speed, and low efficiency. According to those drawbacks, as I said, a couple of decades ago, there was an attempt to try to do something different, and in particular trying to focus the attention on a different kind of physical principle. So the charge carrier are electrodes rather than ions, in order to make to obtain materials more stable, faster, more reliable, etc. And this is actually why those electric elastomers had a big impact, because they actually can combine those advancements, as I'm going to show in a while. So let's enter the details of the electric elastomer actuator. Basically, what we have is just a layer of an insulating elastomer, like a piece of silicone rubber, which is coated with the deformable electrode. Here you see one electrode, there is another one on the bottom you don't see. It's basically form a capacitor, a deformable capacitor that you can charge with an applied voltage. You have a thickness compression and a surface expansion, which produce deformation. So you have the formation of a piece of rubber according to an electrical stimulus. The beauty of this technology is that you basically can use that principle of operation, which is very elementary. And let me say, it has nothing to do with piezoelectricity or electrostriction, if you know them, because here we don't have organized dipoles in the material. The material is amorphous, so it is just a piece of amorphous rubber, okay, which is just electrostatically squeezed by the deformable electrodes. That's it. So the simplicity of this principle of operation is actually its big advantage, because you can actually design new devices that adopt that principle of operation in order to generate different kind of motions. Here we have just a few examples of multiple degrees of freedom bender, or this is a small chamber that pumps fluid. This is a diaphragm, this is a contractile unit, but there are many, many different examples. We have quite extensive expertise, like other groups, of course, in that field. So these electric elastomer actuators have some interesting properties in terms of actuation. As I mentioned, they are very efficient because they are just an electrical capacitor, so the energy is not wasted besides the leakage current in the dielectrics, which is very, very small. They can generate high strains. You have seen, I think you have appreciated from the videos, the large deformation that you can get. The strains can go between 10 to 100%. They are very resistant because they are just made of rubber. They do not generate noise. This is interesting in terms of biomedical applications, because if we go back to the beginning of this presentation, thinking about, for instance, prosthetics, patients do not like the noise generated by the electric motors used on those artificial limbs. And patients also, of course, do not like also the weight, the heavy mass that made those motors. Here, the advantage is that we are using polymers, so the density is slightly higher than water. They also have self-sensing ability because they are capacitors, and if you stretch a capacitor mechanically, you change the energy density stored in the capacitor, so you can read a signal which is a capacitance variation. You can also control the stiffness, this has been demonstrated, and all these properties are combined in a piece of viscoelastic rubber. So, if you remember from the beginning, these are the properties that we are looking for from an artificial muscles. That's why those materials are referred to as artificial muscle materials. From a performance standpoint, of course, I will not enter the details of this table, which compare many different technologies, actuation technologies made of also other kind of polymer materials. I just want to draw your attention on the fact that the electric elastomer nowadays can even exceed performance of natural muscles in several respects: strain, pressure, which stands for stress, efficiency, and so on. So this is really interesting because we have a piece of rubber with a very simple principle of operation that, from a material standpoint, can outperform natural muscles. Of course, there's always a problem. What is the big problem here? The big problem is that those properties come from the material itself, from the basic principle of operation. But when you want to translate those properties into, or transfer them into a device which is properly engineered, usually the side constraints actually reduce the performance. So the role, our role as engineers is to try to make the most out of this technology. Sorry, this video are not working properly because there's a problem of link. By the way, these are just some robots which can be made out of these technologies, just to show the potential of actuation. I would like to focus this presentation on two specific applications because we are developing them in our group, and I think they might be useful as a way to convey the potentialities that the electric elastomer and in general electroactive polymers can provide to the field of biomaterials and tissue engineering. So the first application, the first example, deals with artificial muscles for bioreactors, and particularly in order to obtain electrically stretchable membranes to be used inside a bioreactor where cells can grow while they differentiate. Of course, many of us know very well that all the tissues that in vivo are subject to deformations, significant deformations like muscle tissue, myocardial tissue, and so on, need to be organized in vitro. So during tissue engineering, for tissue engineering devices, they need to be grown under mechanical stress, because the mechanical stress are an essential input that can guide and promote the generation and organization of these tissues. So in order to mimic exactly the same, or as close as possible, the conditions experienced in vivo. So we need a cell stretching device in order to grow the cell in vitro. The state-of-the-art of cell stretchers basically use macroscopic machines where pneumatic systems are used. Flex cell is very popular, one of the most used in many tissue engineering labs worldwide. There are also examples of companies that sell systems equipped with electrical motors, of course. The problems of these approaches are the relatively low accuracy, in the sense that the control of the local stimulation is conditioned by, of course, the controllability of the pneumatic system, and or in the other case, the controllability of the high speed of the electrical motors, which has to be reduced, of course. Well, another issue is the large size of the wool system, or the end effector, so the final system, the final chamber. And this can be a limitation, for instance, in certain conditions of incubation or under microscope and so on. There are also microscopic attempts to develop useful cell structures with microfluidic systems. By the way, the problem is that you still need bulkier external fluidic drivers. So the problem is still there. So our approach, which is of course research in progress, very basic research, so you will realize we are at the very beginning, is to try to use the electrical elastomers in order to combine the actuation function within the membrane that supports the cells. So we do not split actuation and function as two separate units, which is a typical case. The driving unit is a pump somewhere else. No, we want to combine everything within the chamber and actually within the membrane that supports the cells. So the idea is to have a membrane that is coated with compliant electrodes and as an annular shape, and in the middle there is the actual well where the cells are seated. And when we electrically activate the circular membrane, it basically shrinks the radius of the central cell, the central well where the cells are seated, which is entirely soft, so that the cells receive a radial deformation. So this is a structure of the system, and these are videos that show the prototype in action. So basically the electrical elastomer actuator membrane is underneath this layer. This is the central well with water, or in this case a simple test with water, but of course there could be cells in the medium. And so as you can see, we have a radial actuation, so the cells can actually experience a radial compression. Very preliminary studies on the actual ability of this approach to have an effect on the growth of the cell. So after 21 days of growth, so the cell starts to organize on this layer. So this was just a test to demonstrate that the membrane material was actually not toxic for the cells. So they start to create a typical dome of this kind of cells. Moreover, we have a test, a functional test. This test has been made after 21 days of incubation. And on the left hand side, you see a sample without actuation, while on the right hand side, you see a sample with just 4 hours of a slow actuation, cyclic actuation. And as you can see, after 4 hours, something starts, a different pattern starts to be evident. Okay, this kind of tests are very, very preliminary, so I don't have more extensive investigation to show, but just to give you an idea of what we are doing in that direction. Another example, still for bioreactors, let's say, or experiments with cyclic stretching of cells is this one. In this case, we have the cells seated in the same kind of active membrane, so active stretcher, dynamic stretcher, but the cells in this case are observed under atomic force microscopy. And the idea here is to obtain a surface map of the mechanical properties of the cells. So we basically stimulate the cells in different ways in order to study their mechanical response. So this is the experimental setup. We have a conventional atomic force microscope, and underneath we have the chamber with the cells seated in the center, and so that we can stimulate while we observe the system under the microscope. Moreover, in this case, we have also created an array of electrodes, so we have a pattern of electrodes, which allows us to stimulate mechanically the cells in different directions. So we can choose which direction has to be uniaxially stimulated or multi-axially stimulated. In this case, for instance, it was along the horizontal line in order to observe a possible anisotropic response of the cells. So we map the formation of the cells. Here I have a small video just to show, for instance, in this case, the stimulation, as you can appreciate, was along this direction. And as I said, the ultimate goal is to obtain a stiffness map, a regional map of the stiffness of the sample. Another example that I want to show is different. In this case, we are, instead of stimulating the cell over a plane, we are actually stimulating them in a three-dimensional fashion. In order to do that, we have to change the kind of actuation system. In this case, we are using a sort of bubble like this. A bubble, we call it bubble because it is made of a top membrane and a bottom membrane with a fluid in between. So the bottom membrane is actually the deformable electrical capacitor, the real dielectric elastomer actuators. So when you apply a voltage between the two electrodes, these pre-shaped curvature buckles further. And since there is a coupling between the bottom membrane and the top membrane via an incompressible fluid like a gel or water, we actually have a transmission of actuation from the bottom membrane to the top membrane. And you can see here an example. So this is just an actuator. How we can use it to stimulate cells in a, let's say, non-conventional way. Actually, we have devised this structure where we have this actuator that I just showed, which is coupled again to a fluid and a small chamber, soft chamber, where the cells are seated. So the idea is that when the actuator moves up and down, the transmission via the fluid to the membrane, which hosts the cells, is able to impact the cell. So in this case, the cells are not stretched along the plane, but they are deformed up and down, so to speak, or better, the membrane where the cells are seated is deformed as a buckling membrane. And let me show you a video of a prototype in action. Can you see the video, or I need to share it probably? Can someone tell me if you are seeing a video?
We cannot see your video, sir.
Okay. Oh, thanks. So I need to share. Let me switch for a while, sorry, because I need to share the video, otherwise you don't see it. Okay. I don't see how to share it, by the way. I mean, I don't find it as an open file.
Doctor, your screen sharing has been stopped. Can you?
Yeah, I've opened it, but I don't see the. Maybe I share the screen. Let's do like that. I share the screen. Okay. Can you see the video now?
Yes, yes.
Okay, perfect. So you basically see here, you see the top of this device, and you can hear that the cell membrane has been removed, cell chamber, in order to let you see the deformation. But you can imagine that here there is the membrane with the cells, so you have the transmission of motion. So why are we interested on that? Because basically we are interested in studying the deformable tissues, like, for instance, the palm lungs. Okay, in this case, we really need three-dimensional deformations. Okay, so that's why we have devised this is the structure like that, which is, of course, not the only one possible. As I said at the beginning, the beauty of this technology is that you have a basic principle of operation, and then it is our role as engineer to design a structure. This is a possible way to do that, but I'm sure there are also many others. And again, we are doing some preliminary investigation in order to show that, in this case, fibroblasts are able to organize on these 3D deformable shapes, and in particular, they actually feel the strain such that they organize differently if they are grown dynamically rather than statically. So you can see there is a clear organization of the orientation of the cells. Okay, this closes the first part of my presentation. The second part deals with something completely different. Here we are a little bit far away from the tissue engineering field, but I wanted to show anyway those activities because there might be something more on the long term, and they might deal with implantable devices like optical lenses. We are not yet there, so we are still working with something that cannot be implanted today. Of course, there are still many challenges to be addressed. But at least I want to show that there are other opportunities. And in this case, for instance, optics is another interesting field where those smart materials can actually do something different relative to the state of the art. Indeed, when you want to focus light in a conventional optical system, the typical approach is to shift with a motor a stiff lens, like a conventional glass lens, back and forth. So this is what our camera, the cameras in our phone do, or the zoom of our photo cameras actually do. And this complicates the system a lot.
Doctor, sorry to interrupt you.
Yes.
Your share screen has been stopped again. Can you please check once?
Oh, sorry. I assumed it was still okay. Okay, I apologize. So I was actually presenting this, like, can you see it?
Yes, now we can see it.
Okay, thanks. I just mentioned that conventional focusing system actually move stiff lenses back and forth. While if we want to mimic the simpler solution adopted by nature in our eyes, for instance, in our crystalline lenses inside our eye, we need something different. We need that the lens itself is able to change its curvature without any displacement, so without any motor that shifts the lens. So the lens must be functionally active in that, from an actuation standpoint. So in order to obtain so-called electrically tunable lenses, so exactly in that sense, so lenses that can change their focus when they are driven by an electrical signal. The state-of-the-art already offers something. There are piezoelectric driving systems, there are electrowetting lenses, so lenses that basically use two non-miscible, immiscible liquids with a different density. There are also voice coil actuation systems, so basically a soft lens is pushed and pulled by an external motor, basically. There are also examples of hydraulic motion, And there are also more sophisticated systems like system driven with pneumatic liquid crystal that basically are organized by an electric field, or even more sophisticated example like acousto-optic effects. And so I do not have time, of course, to enter into all these details. I just want to draw your attention because each approach has its pros and cons. Of course, there are no magic solutions or no winning solution that can accommodate any need. So there is always a need for something different for one or more properties. So our approach is a real bio-inspired approach, and we try to mimic the functionality of the crystalline lens. Our lens in our eye is basically actuated by some muscles. They're called ciliary muscles that pull the lens. The lens is just a biconvex structure made of gel, basically, which is pulled radially by these muscles. And so you have a soft lens driven by surrounding muscles. Nothing is displaced back and forth. So we want to mimic that. In order to do that, we have considered a soft lens, again, with an artificial muscle surrounding the lens. So the artificial muscle, of course, is a dielectric elastomer actuation membrane, like the one that I've shown before. So according to this very simple architecture, here, this is a cross-section. We have the soft lens. There is a fluid that couples two silicone membrane, for instance. This is the lens. This is a cross-section of the annular artificial muscle that surrounds the lens. So when the two electrodes are charged by an applied voltage, the thickness is squeezed and the surface expands, and so the lens is pushed, is compressed radially. This way, basically, the curvature increases, and so the focus can actually, focal length can be reduced. So in that sense, we have a functional analogy with the principle of operation of the crystalline lens in our eye. And this is a comparison between our artificial lens and the natural lens. This is a prototype in action showing the possibility to focus two different objects, syringe needle and pencil in this case, at different distances. Again, the properties here, the performance already can exceed. Here we are very close to crystalline lens, but actually in the latest prototypes not reported here, we have exceeded the variation of the focal length in the human crystalline lens. So remember what I said at the beginning, that technology is really able to outperform natural muscles. So the challenges come when you really try to engineer the device properly, because there are limitations. In order to increase the focusing speed, moreover, we have used some good elastomers, in particular some silicone elastomers. Also, thanks to a collaboration with a group in Switzerland, we have also improved the fabrication process. And as you can see, we can actually make very, very thin lenses. And the response speed can be as low as 175 microseconds. So this is very, very impressive for a polymer lens, because this is actually the world record for a soft polymer lens. There is no other lens faster than this, completely made of polymers. So this shows that actually many applications can actually be enabled by that technology. You have a piece of polymer that, so very, very, very simple, with a low cost, that can electrically be driven in order to focus light with fast response speed. And for instance, for imaging application, this is very useful. This is just a video showing actually the time, piece of attention, the time. We are in the order of 100 microseconds. Okay. This video, sorry, is not working. In order to trying to lower the sensitivity to vibrations and temperature changes due to the fact that in the lens we are using fluid, we have also shown some versions which are completely made out of solid, so a solid body lens. So in this case, we have shown that we can actually deform as a lens that is completely made of silicon rubber, without any fluid inside. And this is very useful for applications. Moreover, we have shown that we can also do something more, not only changing the focus, but actually changing other optical properties. For instance, astigmatism. This is important because we want to use those lenses at this stage where they are not yet ready for implantable application. We also want to use them as outside of the body in order to correct, actually, in order to obtain some prescription for conventional eyeglasses using a technology which is simpler and cheaper than the conventional phoropter or other systems that are used when you go to the doctor in order to get a prescription for your glasses. You know, the doctor uses some machines, and there is also a subjective part of the test. Well, we want to develop all these equipment and subjective tests, want to combine them in simpler devices, low-cost devices, which can be used in countries that do not have a sufficient number of medical operators that can do the prescription. For instance, think about the certain countries in Africa where there is a critical need of medical operators. Actually, we would like to bring that technology there in order to allow even volunteers, for instance, to help patients to get a proper prescription without the help of trained personnel. So this is an idea, a project that we have just submitted. This technology could actually, make a difference in order to tune not only focus, but as I said, also other features like astigmatism. And in order to convince you out of this is an example of a test of a lens which has two directions where it can be independently activated, either the vertical one or the horizontal one. So you can basically squeeze the lens in these two alternative directions in order to change actually the astigmatism of the lens. As you can appreciate, maybe it is not so trivial, but the central figure is center picture is obtained when the lens is in the natural state, while the right-hand side pictures are taken when you have a compression horizontally only, and as you can appreciate, the lines that are horizontally arranged are more in focus than the lines that are vertically oriented. And this happens also for the zebrafish. The zebra line. Again, here we have the inverse situation. So the focus is the dual one. So this is just to show that it is possible to, sorry, I don't know why, but some videos are not working properly. I just tried them before, but for some reason they are not working now. By the way, you have seen the pictures, and I think they have already conveyed the message. So the conclusions of these two macro areas that I have presented, so tissue engineering and tunable lenses, is that the electrical elastomer actuation can actually add something in terms of new materials, new electroactive materials, polymer-made materials, as artificial muscles. The opportunity especially comes from the possibility of creating deformable substrates, which are electrically driven and offer significant versatility in terms of design, because as you can see, as you have seen, you can change the geometry of your device by simply changing the architecture, and so the function changes accordingly. The lightweight and the thin structure is another added value, of course, The self-sensing abilities have not shown anything for reasons of time, but believe me, self-sensing is feasible. The fast response is another pros, and the low power consumption, especially related to conventional electrical motors. Moreover, they are silent and they do not generate heat, so they do not overheat your samples, for instance, in case of the cells. This is very useful. The future developments concern a major, what I would say is really the most problematic bottleneck of this technology, is the fact that it needs high voltages, in the order of 1 kilovolt today. But be careful. 1 kilovolt does not mean big machines, big driving units, because fortunately the currents needed to drive this technology are in the order of microamps. They depend on the surface and other things, but are in the order of microamps. And so you do not need a huge amount of electrical power to drive them. That's why you can simply drive any of those devices that I've shown today. You can simply drive them with a compact unit like that, which basically uses a conventional battery. Because, as I said, you need high voltages, but you don't need high electrical power. So these are scaring, but in reality, technologically wise, everything reduces to this, okay? By the way, we want to go beyond that, and there are already evidences, actually demonstrations, that in a few years, this technology would be driven at a few hundred volts. So exactly like conventional piezoelectric or retrostrictive actuators. So even in terms of applications, this would be an advantage. Okay, thank you very much for your attention.